as we would expect if we only include the conduction loss, it will actually give us 66%, or according to simulation, 68%. So how can we get more efficiency from the bigger switch? Well, by tuning the switching frequency. If you remember, I selected the switching frequency initially here as 1 megahertz. That's very fast. We should lower the switching frequency when we use bigger switch because it has more switching losses. And so now to how to select the switching frequency of a buck converter. And that's essentially the last design parameters that we need to select in a buck converter. For the switches, we seen the voltage rating, current rating, and the on resistance. Now let's talk about the required switching frequency. Well, the conduction loss decreases as we increase the switching frequency, because remember that if we have a buck converter and this buck converter, both switches are implemented using the same switch with the same R on, so it's always when S1 is on, it sees R on, it sees R on. So in this case, the conduction loss will be essentially the RMS value of the inductor current, because the inductor current will always see R on either top or bottom, times the equivalent on resistance of R on if we're using the same technology or the same FET for S1 and S2. And as you can see, the conduction loss is inversely proportional with the frequency. As also shown in this graph, this is the frequency. You see the conduction loss decreases in proportion to 1 over F as we increase the switching frequency, because the peak-to-peak ripple in the inductor current essentially decreases as we increase the frequency. But the average, of course, doesn't change. On the other hand, the switching loss, which basically is the gate drive loss of both switches, and the output switching loss of both switches, is linearly proportional to the frequency as shown in the blue line. And then the total loss, which is essentially the sum of conduction and switching, will, as shown in gray, will have a minimum point, because the conduction is decreasing while the switching is increasing versus the frequency. So there is an optimal point that minimizes the total loss, switching and conduction of the buck converter, and that should be the switching frequency we select. But as you can see here, this is 10 kilohertz 987. So the optimal for the APC 2031 is 7 kilohertz. Well, our audible range is from 20 hertz to 20 kilohertz. You don't want to build a power supply or a circuit that basically ringing beside the user, right? That can hear it's ringing, right? So you want to make your switching frequency always above 40 kilohertz. Okay, so that you are far away from audible range. And so basically you will see that if we select, say, 50 kilohertz as the minimum, we still achieve a decent lower losses in comparison to operating at 1 megahertz. And so the efficiency increases from 68 when we were at 1 megahertz up to essentially 98.68%. And that's all by selecting the switching frequency as 50 kilohertz. So I like to get an analytical expression for the optimal frequency. And to do that, all we're going to do is we get the P total, conduction plus switching. This is a conduction loss, this is a switching loss. And then take a first derivative with respect to the frequency. This is inversely, the first term is inversely proportional to the frequency, the second is proportional to frequency, equate to 0, to get the point that essentially of 0 slope, or essentially that minimizes the total loss. And you will find that the optimal switching frequency F star is given by this expression. So it depends on the on resistance, or equivalent on resistance, CIS, COS, input voltage, and the VGG. And it also depends on the duty cycle as shown in the graph bottom, and it reaches a maximum value. So the optimal switching frequency will depend on the duty cycle you are using, and it reaches a maximum frequency around a duty cycle of 0.5. So if we recap a little bit, we find that increasing the switching frequency increases the required inductance, which is good. Increasing the switching frequency reduces the required output decoupling capacitance. However, we know that why we don't do that excessively, because increasing these loss the frequency will increase the switching loss of the buck converter or any DC to DC converter, and that's why the ability to develop power converter of smaller volume size, smaller magnetic, smaller capacitor sizes is basically by having better switches, better FETs that essentially can switch at very high speeds and not cause a lot of switching losses or cause lower switching losses. And that's how we move from silicon MOSFETs to gallium nitride and so on. One last point is, as I mentioned, this is a very simplified way to calculate the losses of a buck converter or generally any other converter, just considering the conduction loss and the switching loss. However, there are other more important and actually dominant loss components, but they are a little advanced. One of them is the overlap loss. You can think of the overlap loss is basically the transistor Q2. Once its gate voltage exceeds the threshold voltage, there would be some drain current flowing into it. However, its drain to source voltage was at Vn and is starting to decrease, will take finite time to decrease. So all of this, during this interval, Q2 is carrying finite amount of current and has very large voltage across its terminal, so it will cause high amount of power loss. This is called overlap loss or turn on overlap loss. And also there is turn off overlap loss as we turn off the switch. And the same thing for Q1. So these are very critical loss components. The other loss component related to switching loss that we didn't discuss is that when both Q2 and Q1 are off, right? Both of these are off. Where would the inductor current go? We know that the inductor current is going from left to right, assuming continuous conduction mode. So the only way for it to go is to go in the body diode of Q2. So when it goes through the body diode of Q2, it will cause losses due to the forward voltage drop as well as the diode equivalent series resistance. So these losses, what we call diode conduction loss or reverse loss in gallium nitride devices, both of these are very important components of switching loss. However, they are little complicated to calculate in the first class.